look at is the equation that describes how pressure changes with depth in a fluid. So like I said, with the submarine, the pressure is really big on the outside of the submarine, and that's because of the weight of all that water above it. So we can derive an equation that allows us to calculate the pressure at any depth in a fluid. So for example, let's say we have a swimming pool, a lake, it doesn't really matter, some sort of fluid in some sort of enclosed region. Let's look at the top layer of this water. Now, according to Newton's second law, the net force on that water has to equal the mass times acceleration of that water. But if this is just a stationary swimming pool or lake, that water has no acceleration as a whole. Now, individual water molecules are certainly moving around, but as a whole, the water is not moving around. Okay? So the net force has to be 0. So what forces are acting on that layer of water? Gravity and the atmosphere. So force of gravity, force of the atmosphere. Yeah, force of the water underneath it, pushing up. Now there's certainly forces inwards from the walls of, say, the pool. There's forces inwards. They're not as important in determining the pressure with depth, though, so I won't go ahead and write those. Now the force, all of these forces act over the whole surface. They're not acting at any one given point. Let's go ahead and write our force equation. We have the force of the water upwards. We have the force of the atmosphere downwards. And we have the force of gravity downwards. So basically, the force of the water upwards has to equal the force from the atmosphere plus the force of gravity in order for equilibrium to be maintained. Now, we don't tend to talk about force in and of itself. So let's write these in terms of pressure. How do I go from a force to a pressure?
Area times.
So what's force? Okay. So I'm going to say the pressure from the water times the area for the force of the water. Now this area is the cross-sectional area. So if you were looking down, say if this is a pool, looking down at the pool, that's the cross-sectional area of the pool. Force of the atmosphere is going to be the atmospheric pressure times the area. Now with gravity, we don't tend to talk about gravitational pressure. So we're going to still call it mg. But we don't tend to talk about mass. We tend to use densities instead. What would mass equal in terms of density? So mass would be the density times the volume, right? Yeah, gotta watch the little density versus pressure. So in place of mass, I'm going to put density times volume. Now we can do one more little simplification. The mass of that section of water depends upon the volume of this section of water. Volume If I know the cross-sectional area of the whole thing, what else do I need to know to find the volume?
Height.
How high it is. Okay, I'm going to call that D. So the volume would be the cross-sectional area times that D, the height, however tall that section of water is. So everything stays the same, except for in place of volume, I'm going to put cross-sectional area times D. Which conveniently means we now have a cross-sectional area in every single term. The water pressure at any depth, in this case in the pool, is equal to the atmospheric pressure plus the density of the water times 9.8 times the depth you have gone in the water. This works in any fluid. The pressure at any location, at any depth in a fluid, is equal to the pressure at the surface, whatever that happens to be. If it's open to air, then it's just atmospheric pressure, plus the density of whatever the fluid happens to be, times G, times D, the depth into the fluid you are. So for example, what would the water pressure be 200 meters below the surface in the ocean? So say we're in a submarine. We're 200 meters below the surface of the water. We're out in the ocean. What will the water pressure be at that location? This equation works just fine. This equation works in any fluid. So the pressure at the location we want depends upon the pressure at the surface, but the pressure at the surface is 1 atm, atmospheric pressure. Density. Ocean is not regular water, it's seawater, salt water. Density is a little different. It's on the table in your book. If I remember correctly, it's 1030 kilograms per cubic meter. A little more dense. Not by much, but a little bit more dense than regular water. G is 9.8 meters per second squared. D is our depth, so 200 meters. Now we have to be careful. Unit-wise, this kilogram meter per second squared is a Newton. This meter will cancel out with one of these. So this term right here, this rho GE, is going to give us units of newtons per meter squared, or a Pascal. We can't directly add newtons per meter squared to ATMs. It doesn't make sense. It'd be like trying to add 5 feet to 40 meters. They're not interchangeable. So we need to convert this to Pascals, and then we can add it. Or we can convert this to ATM and then add it. It doesn't really matter. Since I know 1 ATM is 101 300 pascals, I'll just go ahead and do that. Don't know. So that's the pressure. If you wanted an ATM, you could divide it by the 101 300. So this is basically 21 ATMs. So at 200 meters below the surface, whatever object happens to be there is now experiencing an inward pressure of 21 ATMs. So 21 times the atmospheric pressure. So let's say we have a submarine down there. If I took a 1.5 meter squared area of the submarine, what force would that section feel?
The atmospheres or
Well, what's force traditionally in?
Pounds.
Newtons. So we can use our equation here. We know the pressure down there. We know the area. So the force, just rearranging this equation, the force is the pressure times the area. So we simply need to take our pressure there and multiply by the 1.5 meters squared. So that's the inward pressure due to the water. There is some outward pressure on it, because the submarine would have atmospheric pressure inside of it. So there is air pressure pushing out.
just
So-
minus one?
So this is just the force due to the inward. This is just the inward force. If we want to know the net force, we would need to find the net pressure, which is easy enough. The net pressure is the 21 atm minus 1 atm. So 20 atm. Put it into pascals so we get the right units. Multiply by the area. The net force would be 3.04 times 10 to the 6th. These are some very large forces. Yes? I took this pressure times that area. Net force, I took the net pressure. This is the pressure inwards from the water, and I subtracted the pressure, atmospheric pressure that was outwards. So basically I took 21 minus 1, got 20. So the net pressure would be 20 atms. I put it back into pascals, and then multiplied it by the area.
That's, I don't know, is that the net? The pressure will be inside the cell, they make that
One
one
atmosphere.
atmosphere.
It'd be pretty close, yeah. It makes it really hard to breathe if the pressures are significantly different from that. So yeah, the submarines, airplanes, they all try to pressurize the inside to your 1 atm. The whole reason we breathe is because of pressure differences between our lungs and then the air cavity surrounding our lungs inside of our chest. That's the whole reason we breathe. The pressure gets lower inside of your chest cavity, which pulls air in when you push it out. Questions on that example at all?
Big T and little t, I think.
You gotta, it's gonna take a little practice. So capital P is specifically the pressure, the little rho is density. And yes, you'll see both of them quite often in the same equation. So you do need to be careful and remember which one's which, because they're certainly not interchangeable.